The aim of this video is to explain the Nernst equation and how it relates to ions and the ion channels in a cell membrane that they flow through.
In this diagram, a lipid membrane separates two different salt solutions. Two different cations are represented in red and yellow. The cations are balanced on each side of the membrane by a single type of blue anion. You can see that there's a steep concentration gradient of yellow and red cations across the membrane. The membrane is impermeable to all the ions, so they cannot cross over and mix. The red indicator above the membrane illustrates the steep gradient of red cations across the membrane. There's also a steep gradient of yellow cations, but in the opposite direction. But on both sides of the membrane, the total number of cations, red or yellow, equals the number of anions, so there is no charge or electrical gradient across the membrane. The voltage gradient is illustrated in green above the chambers. We'll now put an ion channel in the membrane. This channel is shown in red because it is selectively permeable to only the red cations. When the channel opens, the red ion can cross the membrane, but none of the other ions can. Watch the gauges at the top to see how the concentration and voltage gradients change as red ions move across the membrane. The consequence of selective permeability is that the concentration gradient of the red ion across the membrane falls. At the same time, there's a build-up of positive charge in the left-hand chamber, creating a voltage gradient across the membrane. As the voltage gradient increases, the positive charge in the left-hand chamber repels the movement of further cations. It therefore opposes the concentration gradient that is driving red cations to the left. As a result, the ions don't keep moving across the membrane until they are equally distributed on both sides. Instead, they stop flowing when the repelling force from the voltage gradient equals the driving force from the concentration gradient. The voltage gradient at which that happens is known as the equilibrium potential or the Nernst potential for the ion. To summarise, the equilibrium or Nernst potential for an ion is the membrane potential at which the push from the concentration gradient equals the pull from the voltage gradient, and there is no net movement of ions through a channel or across the membrane. The voltage or membrane potential at which this occurs is described by the Nernst equation. E is the equilibrium or Nernst potential, and it is a function of the ion concentration gradient, which is written as the natural log of the ratio of the extracellular to intracellular concentration. The equilibrium potential is temperature dependent, and this is represented in the equation by T. It is important to remember that in this equation the temperature must be given in units of Kelvin. That is, the absolute temperature. Two of the parameters, R and F, are standard physical constants, the gas constant and Faraday's constant. The valence, or the charge, of the ion makes a major contribution to the equilibrium potential. Both the number and direction of the charge must be included. For example, the valence of a sodium ion would be +1, but the valence of a chloride ion is -1. This table shows the normal concentration gradients for the main ions that conduct current through ion channels in cell membranes. The concentration of sodium ions is low inside the cell and high outside. Applying the Nernst equation gives an equilibrium potential for sodium ions of plus 70 millivolts. As a consequence, when sodium channels open at a normal resting potential of around minus 80 millivolts, sodium ions are driven into the cell to depolarize it toward the very positive equilibrium potential. In contrast, the potassium ion concentration is high inside the cell and low outside, giving an equilibrium potential of nearly minus 90 millivolts. As a consequence, unless the membrane potential is more negative than minus 90 millivolts, potassium ions will always move out of the cell when a potassium permeable channel opens. In all cells, there is a very large concentration gradient for calcium ions across the membrane. Its concentration is held very low inside the cell, but is at millimolar levels outside, so the equilibrium potential is very positive, a voltage that a cell would never reach. So, whenever a calcium channel opens, calcium flows into the cell. The more negative the membrane potential, the greater the driving force and the greater the flux. Chloride ions are interesting. The intracellular concentration can vary enormously from cell to cell, so there is large variability in the equilibrium potential. The consequence is that when a chloride channel opens, in some cells, chloride ions move into the cell and hyperpolarize it, but in others it moves out of the cell and depolarizes it.
The Nernst potential provides a framework for understanding the electrical properties of cells and their significance in biological processes. It is fundamental to explaining the resting membrane potential. Like the Nernst potential, the resting membrane potential depends on two factors: the permeability of the membrane to different ions and the ion concentration gradients across the cell membrane. So, if the resting membrane was permeable to only one ion, the value of the resting membrane potential would equal the Nernst potential for that ion. Unfortunately, cells are not that simple. They are usually permeable to more than one ion, even at rest. In that case, the Nernst potentials of all the permeant ions contribute to the resting membrane potential. In this scenario, the resting potential is described by an extension of the Nernst equation known as the Goldman-Hodgkin-Katz equation, after the people that developed it. Here it is written for a membrane permeable to potassium, sodium and chloride ions. This equation looks more complex than it really is. It's almost the same as the Nernst equation, but repeated for each ion. Since the ions are not equally permeable, the Nernst potential for each ion is scaled by the factor P, which is the permeability of the membrane to that ion.